When you hear the word elasticity, your mind probably jumps straight to a rubber band, right? But the physics behind that simple snapback is actually the same science that keeps massive skyscrapers standing tall and bridges from collapsing into rivers. So let's dive into this incredible world of stretch, squeeze, and snap.
I mean, you've probably done this 1,000 times, just squeezed a stress ball without even thinking about it. But have you ever stopped and wondered what's really happening on a physical level? How does it squish down and then, like magic, pop right back to its original shape? Well, that's the core question we're going to unpack today.
So here's our game plan. We're going to start with that basic snapback idea. Then, we'll get into how scientists actually measure this stuff. We'll look at the fundamental law that governs all stretching, explore the 3 main ways you can actually bend things, and we'll finish up with this really cool side effect I like to call the sideways squeeze. All right, so where do we even begin? Well, it all comes down to a material's amazing, almost magical ability to remember its original shape. Let's break down exactly how that works.
The first term we really need to get our heads around is deformation. Now, I know it sounds super technical, but it's actually really simple. It's just any change in an object's shape or size because you're pushing or pulling on it. Squeezing, stretching, bending, yep, that's all just deformation.
And that brings us to the star of our show, elasticity. This is that incredible property, that kind of material memory that makes an object want to return to its original form once you stop messing with it. When you let go of that stress ball, it's elasticity that's doing all the work, pulling it right back into that perfect sphere.
But, and this is a big but, there's a catch. Every single material has its breaking point. If you stretch a spring way too far, it just stays stretched, right? That's because you've pushed it past its elastic limit. At that point, the deformation is permanent. It's like the material's memory just gets completely wiped.
Okay, so things deform and they snap back. But how can we actually measure this in a scientific way? Well, physicists use 2 really key concepts to figure out the relationship between the force you apply and the change you get. And those are stress and strain.
First up, let's talk about stress. Now, here's the key thing to understand. Stress isn't the force you're applying to the object. No, it's the internal force the object creates to fight back, to try and restore itself. It's the material's own resistance, and we measure it as force over a certain area.
Now, the other side of that coin is strain. Strain is all about measuring how much the object actually deforms, but relative to its original size. So it's a ratio. You might say something like, it's stretched by 10% of its original length. And because it's just a ratio, it doesn't have any units, which is super useful. It lets us fairly compare the strain on a tiny little wire with the strain on a massive steel beam.
So, if we want to put it as simply as possible, stress is the cause. It's that internal pushback. And strain is the effect. It's the actual change in shape. You apply a force, that creates stress inside the material, and that stress results in strain. Simple as that.
Okay, so we've got stress and we've got strain, but how are they connected? Is it just random, or is there some kind of rule? Well, thankfully, for most materials, there's this very elegant and pretty famous law that connects them perfectly. And that is Hooke's law. It's just beautifully simple. It says that as long as you don't go past that elastic limit we talked about, stress is directly proportional to strain. In other words, if you double the stress, you get double the strain. It's a predictable, straight-line relationship. Now, to turn that idea into a real equation, we introduce a constant. We'll call it E, which stands for the modulus of elasticity. You can think of E as a unique number for every single material out there. Steel, for example, has a really high E, while rubber has a super low one. This modulus is basically just a scientific way of saying how stiff something is.
Okay, this is where things get even more interesting. It turns out that stress and strain aren't just single things. Nope, depending on how you apply the force, you get different types. And there are 3 main kinds that we really need to know about.
First, we have tensile stress. This is that classic stretching or pulling force. The perfect example is a rope in a game of tug-of-war. That rope is under some serious tensile stress, and the stretch that results from it, we call that tensile strain.
And the specific stiffness a material has against this kind of stretching, well, that has its own special name too, Young's modulus. So a material with a really high Young's modulus, like carbon fiber, is just incredibly difficult to stretch out.
Next up, we've got volume stress. This is what happens when a force presses in on an object from every direction all at once. The best example I can think of is a submarine deep in the ocean. The immense water pressure is just squeezing it from every single angle. That's volume stress. The material's resistance to this all-around squeezing is measured by something called the bulk modulus. So something with a crazy high bulk modulus, like a diamond, is almost impossible to compress. It just won't budge.
And finally, there's shear stress. This is more of a sliding or a twisting force. I want you to imagine putting a big book on a table and then pushing the top cover sideways while the bottom cover stays put. You're applying a shear stress, and you can see the book deform into a kind of slanted shape. So, how much a material fights back against this kind of twisting or shearing? That's what we call the modulus of rigidity. Essentially, it tells you how hard a material tries to keep its shape from being warped or twisted like that.
So we've covered stretching, squeezing, and shearing. But you know what? There's one last, really fascinating effect we need to look at. It's this weird little side effect that happens anytime you stretch something.
Just think about it for a second. Take a rubber band. When you pull on it to make it longer, what happens to its width? It gets thinner, right? Of course it does. It doesn't just stretch in one direction.
Well, there's a name for that. This whole phenomenon is described by something called Poisson's ratio. It's just a single number that measures this sideways squeeze. It's the ratio of how much the material thins out compared to how much it lengthens. It perfectly captures that trade-off between getting longer and getting thinner.
So there you have it. We now have the language to describe exactly how things bend and stretch and squeeze. It's this whole universe of stress, strain, and the specific moduli that define the strength of literally everything around us. Which kind of leaves you with a final thought, doesn't it? If we wanted to build something truly incredible, something like a space elevator, what kind of material would we even need? What perfect combination of Young's modulus, rigidity, and Poisson's ratio could possibly handle that kind of stress?